Hello everyone, welcome to OATS Institute. I am Aliakbar and I am thrilled to have you here for this knowledge-rich journey into the world of power electronics and electric vehicle. Today we are going to unravel the fascinating world of power electronics and how it plays a pivotal role in the evolution of electric vehicles. Whether you are a mechanical, automobile or electrical engineering student, this lecture is tailor-made for you. So let's dive right in and unlock the secret of power electronics and electric vehicle. Now before we dive into the heart of power electronics and electric vehicle, let's take a structured approach to ensure you know what to expect from this video and to keep you engaged throughout this lecture. First, we'll start off with what power electronics are and their essential role in the world of electric vehicle. Next, we'll explore various types of power electronics used in modern electric vehicle. Next, we'll focus on three key types of power electronics and we'll show you how these components work in harmony to power your electric vehicle efficiently. We'll also discuss the practical aspect of power converter design consideration, showcasing the key factor that engineers consider when designing power electronics. And lastly, to make things even more relatable, I will provide real-world examples of electric vehicles that utilize this technology. So, let's begin with the first topic. The first power electronic system introduced by Peter Cooper-Hewitt in 1902 marked the initial step in the journey of innovation. It featured a mercury arc rectifier, a groundbreaking invention that converted alternating current into direct current. This laid the foundation for what we know today as power electronics. Fast forward to the late 1940s, and we witness a pivotal movement with the invention of the first transistor. This was the birth of modern power electronics. Since then, the performance of power converters has continually improved. This progress is attributed to advancements in critical components like switching devices, magnetic materials, and cooling solutions, to name just a few. Now, let's define what power electronics truly represent. It's a technology that enables the effective management of electrical energy. In an electric vehicle, electric traction motors are at the heart of the operation, providing the mechanical power that propels the wheels. The energy that fuels this electric motor can either be stored in an electrochemical energy source like a battery or ultracapacitor, or generated by the vehicle's engine in case of hybrid electric vehicle. Therefore, to set this motor in motion, we need to transfer energy from the onboard energy source to the motor. But it's not just about moving energy from point A to point B. This energy must be transformed in a controlled manner. The goal is to create a rotating magnetic field within the motor precisely tailored to meet the specific load requirement. The seamless orchestration of these phases, including energy transfer, transformation, and control, is made possible by power electronic systems. These systems are the silent heroes working behind the scene to ensure the electric vehicle operates with efficiency and precision. Power converters, a critical component of power electronics, plays a pivotal role in this process. They not only convert electrical energy but also manage the power flow throughout the vehicle. This power flow can be in various directions, whether it's from the battery to the wheels, from the grid to the battery, or even from the engine to the battery or wheels in case of hybrid electric vehicle. Now that we have established the fundamental role of power electronics in electric vehicle, it's time to delve in and explore the different types of power electronic system that makes electric vehicle work seamlessly. The first key player in our lineup is the switch mode DC2DC converter. This remarkable device plays a vital role in regulating and converting electric power within an electric vehicle. They allow for efficient transfer of power between various components, ensuring that the right voltage level are delivered when needed. Moving on, we have the switch mode DC to AC inverters. These devices are essential in converting the DC power stored in the vehicle battery into AC power, which is what most electric motors run on. Lastly, we have the switch mode AC to DC converters. They serve a critical role in transforming the grid's alternating current power into the direct current power required for charging the electric vehicle battery. These components operate with remarkable efficiency and precision, ensuring that the electric power within the electric vehicle is always optimized for performance. Now, let's take a closer look at the first type of power electronics in electric vehicle, switch mode DC to DC converter. These devices play a pivotal role in efficiently transforming one voltage level into another within an electric vehicle. Essentially, a DC to DC converter enables the generation of a controlled output DC voltage from any input DC voltage. In simpler terms, it's like having the power to transform a DC input voltage into a different DC output voltage. Depending on the type of DC to DC converter, the input voltage can either be stepped up or stepped down. The choice of the output voltage value depends on the specific application. For example, in aerospace system, you might encounter voltages like 28 to or 540 volt, whereas in hybrid electric vehicle, the range can be between 225 to 650 volt. Another vital application of the DC-to-DC converter in an electrified vehicle is the creation of auxiliary power unit to supply the low voltage 12 volt DC grid. This grid powers all the electronic components of the vehicle, including the air conditioning system, microprocessor or lighting. In a switch mode DC-to-DC converter, the term switch refers to the fact that the converter incorporates at least one switching device. This device is a semiconductor component that either allows or interrupts the flow of current through it. You will come across various types of DC-to-DC converters, each with its unique advantages or application. Let's touch on a few of these. First is buck converter. A buck converter is designed to step down the input voltage. In an ideal scenario, the relationship between input voltage and output voltage is given by the equation output voltage is equals to D times input voltage, where D represents the duty cycle of the switch. The duty cycle can range from 0, where that is when switch is always open, to 1, when switch is always closed, allowing the output voltage to vary between 0 and the input voltage. On the other hand, the boost converter steps up the input voltage. In an ideal scenario, the relationship between input voltage and output voltage is given by the equation output voltage is equals to input voltage over 1 minus D, where D represents the duty cycle of switch. Theoretically, this equation suggests that the output voltage can be boosted to infinity when the duty cycle is 1, that is when switch always closed. However, practical limitations such as parasitic resistive element in a circuit caps the maximum output voltage achievable by the converter. Lastly, we have the buck boost converter. As the name implies, it can either step up or step down the output voltage. According to the ideal switching scenario, the relationship between input voltage and output voltage is given by the equation output voltage is equals to D times input voltage over 1 minus D, where D is the duty cycle of switch. This equation reveals that if D is less than 0.5, output voltage will be less than input voltage, and the converter operates in buck mode. Conversely, if D is greater than 0.5, output voltage will be greater than input voltage and the converter operates in boost mode. In theory, the ideal buck boost converter can theoretically generate infinite output voltage where D equals 1, that is when switch is always closed. However, as with the boost converter, practical limitations such as parasitic resistivity prevents this in practice. These DC-to-DC converters are the wizards behind the curtains, ensuring that the voltage levels are precisely tailored for electric vehicle system. Now, let's shift our focus to another integral component of power electronics in electric vehicle, that is switch mode DC to AC inverters. These devices play a vital role in the transformation of DC power from the vehicle's battery into the alternating current power that electric motor require. Here's how the switch mode DC to AC inverters work. The switch mode inverters uses transistors like switches to rapidly turn the DC power on and off. These transistors switch on and off really quickly, like thousands of times per second. This rapid switching is known as pulse width modulation or PWM. Imagine a light switch that flickers very fast to control the amount of light. That's what PWM does, but with electricity. By changing how long the switch is on, that is its duty cycle, the inverter can create different voltages and frequencies just like AC power. By controlling the PWM, the inverter generates a series of pulses, which when smoothed out looks like a sine wave. A sine wave is the smooth wavy pattern of AC power, and that's what electric motors of an EV likes to see. So in essence, switch mode DC to AC inverters are like electrical shapeshifters. They take the steady flow of DC power and convert it into the back and forth AC power that electric vehicle needs. The DC to AC inverters come in various forms, including single phase and three phase inverters, each serving specific purposes in electric vehicle. So let's explore them one by one. First is single phase inverters. Single phase inverters are designed to convert the DC current or direct current power from the vehicle's battery into a single phase alternating current output. Single phase inverters are often used in microgrid application. These inverters are used to drive single phase AC motors in some components of the vehicles like air conditioning or power steering systems. Now, let's talk about three phase inverters, which are slightly different but equally important in electric vehicle. Three phase inverters, as the name suggests, convert DC power into three phase AC power. Three-phase AC power is a bit more complex than single-phase and is commonly used for high-power application. This means that they can transfer energy from your vehicle's battery to the electrical grid. It's especially useful when you want to sell excess energy back to the grid or provide power to your home during a blackout. The other main application of three-phase inverters in electric vehicle is for the three-phase AC drive system. Many electric vehicle uses three-phase AC motor for propulsion. These motors are highly efficient and provide the necessary power for automotive, railway or ship application. Both single-phase and three-phase type of inverters play a crucial role in making electric vehicles work efficiently and effectively. Now, moving on to the third type, that is switch mode AC to DC converters. Switch mode AC to DC converters are essential component in electric vehicle that efficiently transform AC power into DC power. Let me explain how they work in the context of EVs. In an electric vehicle, we typically have two sources of power: the AC power from the electrical grid, especially when we are charging the EV, and the DC power from the vehicle's battery. Electric vehicles primarily use DC power to operate control electronics of the vehicle and charge the battery. However, when we plug our EV into a charging station or use a home charger, we are getting AC power from the grid. This is where the switch mode AC to DC converter comes into play. A switch mode AC to DC converter takes the incoming AC power and transforms it into the DC power required to charge the vehicle's battery and operate its systems. Here's how a switch mode AC to DC converter works. The incoming AC power is first rectified, which means it's converted from the AC sine wave, which fluctuates between positive and negative voltages, into a pulsating DC voltage. This is achieved using a component called a rectifier. The pulsating DC voltage is then smoothed out using capacitor to create a more stable DC voltage. This makes it more suitable for charging the battery and powering the vehicle's electronic. The converter also ensures that the DC voltage is at the desired level. In an electric vehicle, this is usually around 400 to 800 volts for the high voltage battery. The converter adjusts the voltage to match the vehicle's requirement. The key to the efficiency of a switch mode AC to DC converter lies in the control of its switching component, typically transistors. This transistor switches rapidly on and off to manage the voltage and maintain the desired output. The duty cycle, which dictates how long the transistor is on versus off, is carefully regulated to achieve the correct output voltage. The AC to DC converter can be categorized into single-phase AC to DC converter and three-phase AC to DC converter, each serving specific purposes in electric vehicle. So, let's explore them one by one. First is single-phase AC to DC converter. In a single-phase AC to DC converter, the input power is provided by a single-phase AC source. In a basic setup, a diode is used for rectification, creating a half-wave rectifier that allows only one half of the AC sine wave to pass through, resulting in a pulsating DC output with gaps. For more efficient conversion, a full-wave rectifier can be employed, utilizing 4 diodes to convert both the positive and negative half of the AC sine wave into DC. This results in a smoother output. Single-phase AC to DC converter are commonly found in smaller electronic devices and applications that require low to moderate power. In a three-phase AC to DC converter, the input power comes from the three-phase AC source, which is a more common setup in industrial and high-power applications such as electric vehicles. In most cases, a three-phase AC to DC converter uses full-wave rectification, ensuring all three phases contribute to the DC output. This results in a smoother and more constant DC voltage. Now, before we continue to our next topic, let's take a moment to understand the role of power electronics through a flowchart. This will illustrate how different configurations contribute to the smooth operation of electric vehicles and make the driving experience both seamless and futuristic. Beginning with the charging process, whether through a residential AC power socket or dedicated charging stations, the initial input is AC power. Power electronics manages this phase using a three-phase AC to DC converter. Its primary function is crucial. It transforms incoming AC power into DC power ready to recharge the electric battery of an electric vehicle. Moving on, when it comes to powering auxiliary systems such as air conditioning or power steering, power electronics employ single-phase DC to AC inverters. This device ensures the effective operations of essential EV functions. To supply power to the low voltage 12-volt DC grid, energizing components like microprocessor and lighting, power electronics incorporate a DC to DC buck converter. This component plays a vital role in optimizing the efficiency of low voltage electronic systems. In the final stage, where the propulsion of the EV is powered by a three-phase AC motor, power electronics once again takes center stage. An onboard 3-phase DC to AC inverter is utilized to convert the DC power sourced from the battery into the required 3-phase AC power, propelling the vehicle forward. In summary, power electronics seamlessly manages various configurations to deliver an efficient EV ride. From charging to auxiliary systems, low voltage grids and motor propulsion, each element is handled with precision to enhance the overall driving experience. Now, before we dive into the practical aspect, let me share some interesting thing about the company who have graciously sponsored this video and who is revolutionizing the way students like you navigate their academic path. Whether you are struggling with assignment, project or thesis work, or in need of a perfect tutor who understands your academic requirement inside out, the Scholars Club has got you covered. With just a sign up, you unlock a world of possibilities. Fill out your academic detail and budget, and their cutting-edge machine learning platform will do the rest. Watch as your requirements spread across the platform, attracting the perfect tutor who's tailor-made for you. It's like magic, and all-in-one experience where you can choose from a pool of proposals sent by the tutor or manually search for the ideal tutor using the state-of-the-art search engine. And now, here's the best part. Visit thescholarsclub.com or download the user-friendly app from the Play Store or Apple Store. Your academic success awaits. Now coming back to our lecture, having understood what power electronics is and what are its types, let's move on to our next topic, which is understanding the practical aspect of power converter design. When engineers design power converters for electric vehicle, they need to create efficient systems that convert and control electrical energy. This is crucial for the proper functioning of the vehicle. Power conversion processes are not 100% efficient. There are always some energy losses. Engineers work to minimize these losses to maximize the efficiency of the electric vehicle. Following are the key aspects that the engineer considered for designing. First is conduction losses. Conduction losses occur when electric current passes through semiconductor devices such as transistors and diodes. These losses are primarily influenced by two factors. First is semiconductor material. The choice of semiconductor material significantly impacts conduction losses. Silicon has been widely used, but newer materials like silicon carbide and gallium nitride offer lower resistance, reducing conduction losses. Engineers select the appropriate semiconductor material based on its specific characteristics and the requirement of the power converter. Second is current rating and voltage rating. The current carrying capacity and voltage rating of the semiconductor devices are important design considerations. Properly matching this parameter to the application reduces conduction losses. Additionally, using devices with a lower on-state resistance helps minimizing losses. Now moving on to the second key aspect that an engineer considers for designing is switching losses. Switching losses are incurred when semiconductor devices transition between on and off state. Engineers focus on several strategies to minimize these losses. First is switching frequency. The switching frequency of the power converter is a critical parameter. Higher frequency can reduce the energy wasted during each switching cycle, but they can also increase switching losses due to faster transition. Engineers strike a balance between achieving efficient power conversion and managing switching losses by optimizing the switching frequency. Second is soft switching technique. Implementing soft switching technique like zero voltage switching and zero current switching can significantly reduce switching losses. This method ensures that semiconductor devices switch under minimal voltage and current stress, thereby decreasing losses. Third is optimized gate drive. Precise control of the gate signal for semiconductor devices is crucial. Using gate driver circuit that minimizes switching times and provide adequate voltage level for efficient transition can help reduce losses. Now moving on to the third key aspect that an engineer considers for designing power converters is magnetic component losses. Inductors and transformers are vital components in power converters, but they are not without losses. Key factors in managing these losses include first, core material. The choice of core material significantly impacts losses in inductor and transformers. Soft magnetic material with low hysteresis and eddy current losses are preferred to minimize core losses. Second is winding design. Engineers optimize the winding design to reduce copper losses, which results from the resistance of the wire used in the coil. Strategies may include selecting the appropriate wire size and minimizing the length of the wire to reduce resistive losses. Third is operating frequency. The operating frequency of the power converter affects the losses in the magnetic component. Higher frequencies can lead to increased core and copper losses. Engineers carefully select the operating frequency to balance between efficiency and losses. In the design of power converters for electric vehicles, efficiency is the paramount consideration. Every effort is made to minimize conduction and switching losses in semiconductors, as well as losses in magnetic components. By switching the right material, optimizing component characteristics, and employing advanced control techniques, engineers can maximize the efficiency of the power conversion process, directly enhancing the vehicle's performance and range. Now, moving forward, let's showcase some current day examples of modern electric vehicles and highlight the type of power electronic configuration they use. First is Tesla Model 3. The Tesla Model 3 employs a sophisticated power electronic setup that includes the switch mode DC to DC converters, switch mode DC to AC inverters, and switch mode AC to DC converters. Tesla is known for using silicon carbide technology to enhance the efficiency of its power electronics component, reducing conduction losses. Their power electronics play a crucial role in optimizing the performance and range of their EVs. Second is Nissan Leaf. The Nissan Leaf, a popular electric vehicle, also utilizes a comprehensive power electronic system. It includes switch mode DC to DC converter for efficient voltage conversion and control, as well as switch mode DC to AC inverters to power the electric motor. Nissan incorporates advanced control techniques to manage switching losses, thereby enhancing the overall efficiency of the vehicle. Third is Chevrolet Bolt EV. The Chevrolet Bolt EV features a power electronic system that includes switch mode DC to DC converter and switch mode DC to AC inverter. These components are designed to efficiently regulate the flow of electric power, making the vehicle more energy efficient and extending its range. Fourth is Audi e-tron. The Audi e-tron uses a sophisticated power electronic setup including switch mode DC to DC converter and switch mode DC to AC inverters. Audi places a strong emphasis on the control of switching components, optimizing switching frequency, and employing advanced gate drive techniques to reduce losses, thus enhancing the vehicle's efficiency and performance. Fifth is Hyundai Kona Electrics. The Hyundai Kona Electrics incorporate power electronic components such as switch mode DC to DC converter and switch mode DC to AC inverters. Hyundai engineers have focused on minimizing conduction and switching losses by selecting appropriate semiconductor material and employing soft switching techniques. These are just a few examples of modern electric vehicles that employ various power electronic configurations to maximize efficiency, improve performance, and extend range. Each manufacturer utilizes specific strategies and technologies to design power electronic systems that are tailored to the unique requirement of their electric vehicles, ultimately contributing to the growth of the electric vehicle industry. And that, my friend, brings us to the end of an amazing power electronic journey. I hope you gained valuable insight into the world of power electronics and its pivotal role in the realm of electric vehicle. If you found this lecture informative and engaging, I encourage you to show your support by hitting that like button and sharing it with others who might benefit from this knowledge. But most importantly, don't forget to subscribe to our channel, OATS Institute. By subscribing, you will stay updated on the latest insight, educational content, and exciting journeys through the world of innovation and technology. Thank you for being a part of this educational experience, and we look forward to sharing more knowledge with you in the future. Until then, stay curious, stay innovative, and stay tuned to OATS Institute. I am Aliakbar, signing off.